In this video, we'll discuss more about integrals. Let's recall the definition, right? So we have the definition of definite integral. To define an integral, we need a function. F is a function. We need a closed and bounded interval, right? So what you do here, let's just look at the x-axis. So this is our x-axis. This is from A to B. You have a function over the interval. What you do here is you divide your interval into subintervals. This is x0, x1, x2, evenly, right? You choose one of them, which is xi minus 1 to xi, where our xi is a plus I times delta x. And delta x is a width of each subinterval b minus a over n here. And from here, right, I here is from 0 to n, and the first one is called x0, and the last one is called xn here, right? Then you choose a arbitrary sample point inside this subinterval. We call that xi star. After you have the xi star, you can calculate f of xi star times delta x, right? So for each I, you can calculate this product. So sometimes that's an area rectangle, sometimes that's a negative area rectangle. Then we take a summation I from 1 to n here. And that's basically, if you have f is positive, this is basically a good approximation of the area of the region under the curve, right? I would take a limit, let n here go to infinity. So if your function is positive, this approximation is getting better and better as n getting larger and larger, right? So this is if the limit exists. This is the integral of f over the interval AB, right? Provided if the limit exists. So this has many applications. So our first natural question is, for what kind of function this limit exists? So the first result theorem says if your function is good, right? If f is right, the function we're interested are always continuous. If a function here is continuous on AB, you don't have any bad points, or you have only finite many bad points, or f has only finite many number of jump discontinuities. Right, what's the meaning of that is the at this point, let's call that C, right? This function doesn't go to infinity, but you have a left limit and right limit are both finite numbers, right? Only finite is kind of this C here is jump this continuity, right? So you only have finite many of them. Then our conclusion here is then f is integrable, which means the limit integrable, the limit exists as a finite number over the interval AB. The limit exists as a finite number. And so if you have the limit exists, now the next natural question is, how do we evaluate it, right? You don't want to choose an arbitrary sample point, you want to fix one. So theorem, this one here says, really doesn't matter which one do you choose. You can choose the right endpoints. If f is integrable, integral just means the limit exists as a finite number on AB, then integration from A to B, f of x dx, right? Definition is, look at our definition here, you choose a sample point, right? And this theorem says you don't need to choose a arbitrary sample point. All you need to do is look at the right endpoints, or left endpoint doesn't matter, but here we just write down the right endpoints, dx, where delta x is b minus a over n, and xi is a plus I times delta x. So that's basically when a derivative, when a function is integrable, and if a function is integrable, how do we evaluate it, right? I use our definition. We don't have to choose a sample point. We'll just choose the right endpoint. That would be good. And let's see some good properties, right? Based on this evaluation method, we can write down a few properties. Properties of definite integrable, definite integrals. And the first one here is integration from A to B, f of x dx. And for sure, we are assuming the function is integrable on the things we're interested, right? And now sometimes we can switch the lower bound, upper bound from B to A, f of x dx, right? Look at what you have here. The only thing change is this. One is b minus a, the other one is a minus b, right? Their difference is negative sign. So as we imagine, it should be minus that. Second, integration from a to a, no matter how complicated the function is, the delta x will be a minus a over n, which is 0. So everything will be 0. So this limit is 0, right? And the third one, integration from a to b, c times dx, c dx, right? And this is basically, if you have c is positive, this is corresponding to the area of a rectangle with base to be b minus a, height is c, right? So this should be c times b minus a, right? So basically integration of 1 will be b minus a, right? A special example, integration from a to b, 1 times 1 dx is b minus a, the length of the interval, right? And some other properties, integration from a to b, f of x plus g of x dx, right? And using our property of summation, you can always split it. So this is integration from a to b, f of x dx, plus integration from a to b, g of x dx. Same thing happens for the difference. If you have a difference of two functions, if both integral exist, then the equation of the difference will be from a to b, f of x dx, minus integration from a to b, g of x dx. One more example here is integration from a to b. If you have c times f of x dx, go back to our definition here, right? That not the way to evaluate integral. C will be a common factor. We can bring that out. So this will be c times integration from a to b, f of x dx, right? That's good. Sometimes make it easier. And right, and let's see one more property, property 5, right? Sometimes your function is easy to integrate on one piece. Right, this is a function y equal to f of x, right? You can see that there's a special point c here, right? So this function for sure is integrable. And sometimes you want to integrate it separately, right? So you can split it. So integration from a to b f of x dx equal to integration from a to c f of x dx plus integration from c to b f of x dx. Or you can combine them if you want, right? You can use both directions, either combine or separate it. Okay, now let's see a quick example, right? First example, again, we want to use the interpretation of integration in terms of area to evaluate this. -3 to 3, 1 minus square root 9 minus x squared dx, right? Okay, so by our property, this function for sure very complicated. We want to split it. By the properties of integral, we can make it from -3 to 3, 1 dx, and minus integration from -3 to 3, square root of minus x squared dx. The first one, we try to interpret this as an area. The first one here, if you try to sketch it, so that's basically rectangle, right? From -3 to 3, and the height is 1, right? So the first term is the area of the rectangle, so you get 3. And second term here, by our discussion before, you get a y equal to root 9 minus x squared. You get y squared equal to 9 minus x squared. You get x squared plus y squared is 9, so that's a circle with radius 3. And because y here is positive, so that's the top half of the circle, -3 to 3. So the second term here is basically the area of the half circle. So this is -1/2 times pi times 3 squared, right? This is a way to evaluate this this integral in terms of areas, right? Let's see one more example. Let's try to use our method to evaluate, use our definition method to evaluate this integration. We want to evaluate integration from -2 to 0 to x plus 1 dx, right? Using this, right, we just mentioned, using the fact integration from a to b f of x, because the function is continuous, so duality will always exist. If the duality exists, you can use this n go to infinity summation f of xi delta x I from 1 to n. Let's try to use that to evaluate this limit, right? And so let's try to do that, right? So we divide -2 to 0 into n sub intervals, right? And from here you can see that delta x will be 0 minus -2 over n, right? Xi will be -2 plus I times delta x. Delta x is 2 over n, right? So let's try to plug the information into here, to simplify the Riemann sum first, right? Summation I from 1 to n f of xi times delta x. Delta x is 2 over n. I will be -2 plus 2i over n, right? So this is equal to summation I from 1 to n here, 2x. So you get 2 times -2 plus 2 times I over n, and then plus 1. Then time delta x, which is 2 over n. Right, so that now we want to simplify this function. We want to simplify this function, right? As a simplify this term into a function of n, then we evaluate the limit as n goes to infinity, right? So common factors first. So this is 2 over n is a common factor. So summation I from 1 to n, because I is a variable, others doesn't change. You get -4 plus 4i over n, then plus 1, right? And so this is 2 over n summation I from 1 to n here. You get -3, then plus summation I from 1 to n here, 4 over n I is changing, 4 over n is not changing, right? And the first term by our discussion of summation is -3 times n, right? 2 over n here. 2 over n, not 2 over 3, right? 2 over n. Then plus 4 over n summation I from 1 to n I, right? By our discussion before, we know that summation I from 1 to n I is n times n plus 1 over 2. So that's something we know. So this is, now we want to simplify our function. So this is -6, then plus 8 over n squared times n times n plus 1 over 2. Right? And so this equal to -6 plus 4 times n plus 1 over n squared. So integration from -2 to 0, 2x plus 1 dx is basically the limit as n goes to infinity of the Riemann sum, -6 plus 4 times n times n plus 1 over n squared, right? So the second term is infinity over infinity. You can apply L'Hopital's rule, so you get 4 there, right? This is -6 plus 4, so which is -2. So that is the way to evaluate an integral using our using the definition methods, right? You can see that very complicated, but we do want to know how to apply definition to evaluate the limit of integrals.